Hi, back again to finish up lesson 3. The previous video we worked through this example where we were looking at heights of women and we were asked how many standard deviations away, and we found out 71.1, 56.1 to 71.1 was 3 standard deviations away. That corresponds to 99.7%. So the answer, I gotta cut that off, was 99.7% was the answer we were looking for. So we're going to continue on. We're on page 19, about halfway down. Going to work on this problem. Again, we have a bell-shaped distribution. That means we can apply the empirical rule. So 1 standard deviation, 2 standard deviations, or 3 standard deviations corresponds to 68, 95, and 99.7. And we're dealing with a mean voltage of 125 and a standard deviation of 0.3. Okay. And we want to use the empirical rule to find the approximate percent between 124.4 and 125.6. Okay, so let's just attack this a slightly different way. I know that the mean is 125, and I know that we're looking for a lower bound of 124.4. So I'm going to go ahead and just take 125 minus 124.4 and just figure out how far apart those are. And so I could just do this in my head. That's 0.6 below. Well, the standard deviation is 0.3, and we're 0.6 below, so 124.4, well, that has to be 2 standard deviations below. Oops, that's an L. Okay, so 2 standard deviations below. Maybe this is 2 standard deviations above as well. So if I took 125 and subtracted that from 125.6, that's equal to 0.6 as well. So the empirical rule states that 95% of the observations are within 2 standard deviations, and I have 2 standard deviations here on both sides. And so the answer here is 95%. Okay, so a similar thing down here. Now I'm even further away. If I took 124.4 and subtracted 1 standard deviation, that's going to get me to 124.1. Okay, so here I was at 2 standard deviations. I subtracted another 1. So 3 standard deviations below the mean. And here 3 standard deviations above the mean. 0.9 above the mean of 125. That's 3 standard deviations because the standard deviation is 0.3. So the answer here is 99.7%. So that's it for the empirical rule. Hopefully we'll have maybe try to get one more example of that in. And we're going to move on down to what we call z-score calculations. And a z-score is all it's doing is calculating the number of standard deviations above or below a value is from the mean. And so the formula for a z-score is right here. X is the observation you are interested in. Mu is the Greek letter mu for mean for the population, and sigma is the Greek letter that we use for standard deviation. I'll just write standard deviation like that. Okay, so we take the value we're interested in, find the distance from the mean, and subtract, divide by the standard deviation. And so what that does, it counts the number of standard deviations above or below the mean. So above would be positive number for the z-score, and below would be a negative number for the z-score. So if you know the mean and standard deviation, then you can calculate a z-score for any observation that you're interested in. And the reason we use z-scores is we want to do what's called standardize a value. And so one pretty easy example to understand is sometimes you take the SAT for your college prep, sometimes you take the ACT. And so a college committee that decides whether you get accepted or not needs to compare your ACT score to someone else's SAT. And so they do that by calculating the standard deviations away from the mean that a student scored. Okay, so that's just one example why we would want to calculate a z-score. So here's an example for us to work through. Michael Jordan is 78 inches tall and Rebecca Lobo is 76 inches tall. So obviously Michael Jordan is taller than Rebecca, but what if we wanted just to compare to their own population? So is Michael Jordan taller with respect to the male population than Rebecca Lobo with respect to the female population? So which player is relatively taller? So what we need to know is the heights of men and women, the mean heights, and the standard deviation of both. And so we're given that information. For men, there's a mean of 69 and standard deviation of 2.8. And for women, a mean of 63.6 and standard deviation of 2.5. And we're going to compare the two heights by calculating a z-score for both. So we'll go ahead and do Jordan first. So his observation, his observed height is 78, and we subtract the mean, which for men is 69, and we divide by the standard deviation for men, so that's 2.8. So his z-score is 3.21, and so his height is 3.21 standard deviations above the mean for males. We'll do Lobo's height second. So her observed height is 76. The mean for females is, 63.6. And the standard deviation for females is 2.5. So her z-score turns out to be 4.96. And so her height is almost 5 standard deviations above the mean. And so if we're going to compare the two, then Rebecca would be taller. Since her height is more standard deviations above the mean. Let's just write SD above the mean. Okay, so pretty simple to calculate a z-score and gives us a way to compare two people from a different population. So males and females, SAT scores to ACT scores and things like that. We're always interested in identifying unusual values. And we know that because we have the empirical rule, if it's a normal distribution, observations, 95% of them should be within 2 standard deviations. So that represents -2 for a z-score and a +2. So 95% should be within 2 standard deviations. And so this is how we come up with this rule for unusual and usual values. And based on our z-score, for Michael Jordan was 3.2 and Rebecca Lobo was 4.96. We already said that she's taller, but they were both be considered unusual because their z-scores are so high. So based on this, are their heights unusual? And so the answer would be yes, since both z-scores are greater than 2. Okay.